So welcome back everyone for this tinyML talk. This is presented today by Nitin Chawla, Fellow and Director STM Microelectronics, and the title is Empowering the Edge: Advancements in AI Hardware and In-Memory Computing Architectures for tinyML. Welcome, Nitin. All our talks are actually supported by the partners, and these are our strategic partners: AIZIP, Analog Devices, Arduino, ARM, Brainchip, Edge Impulse, Efficient, Greenwaves Technologies, Gravity Incorporated, IMAX, IBM, Imagimob, Infineon, Inantera, Microsoft, Nota AI, NXP, Pauline Technology, Quixo, Qualcomm, Renesas, Schneider Electric, SenseML, Sony, Silicon Labs, STM Microelectronics, Synaptics, Sentient, and TDK. Don't forget to join this tinyML communities. We are there on Meetup, we are on LinkedIn, and we have a very vibrant community of 16,000 members in Meetup, 49 groups in 41 countries, and we have 4,000 members in LinkedIn and more than 30K followers. Do subscribe to our tinyML YouTube channel. We update all our videos there, and you don't have to miss anything. You can subscribe to the channel and also like the videos. We have around 10,000 subscribers, 621 videos now, and 361,000 views of them. We have an in-person tinyML Asia Technical Forum, which is happening in November 16, 2023 in Seoul, South Korea. And the call for presentations posters are out. The deadline is August 7. You can scan this QR code and you can go to the link and see the more details. The 2023 Edge AI Technology Report is out. So it is the way to understand the state of the art in hardware and software in Edge AI. So brief about Nitin Chawla. Nitin Chawla is an ST Fellow and Director in Technology, R&D Strategy and Innovation at STM Microelectronics. He leads the research initiatives in area of low-power neural networks and in-memory computing architectures for Edge and tinyML applications. Nitin has a major in electronic circuits and systems. He is an alumnus of Stanford University and holds a TRIS diploma from Massachusetts Institute of Technology, Cambridge. He has served in different R&D and product organizations over the last 25 years. Before joining ST Microelectronics, he was the chief scientist of the HLS product division at Mentor Graphics, based in Oregon, USA. Nitin has over 40 US patents and more than 30 conference and journal publications. Thank you, Nitin. Very happy to have you here.
Thank you, Gitesh, for the kind introduction. And good morning, good afternoon, good evening, everyone. My talk today is going to actually use a case study for motivation in terms of using evolving architectures for neural processing unit, where the focus is energy efficiency. These are going to look at workloads which are low power and ultra low power, but also have the capability to scale up performance on demand. This is obviously a joint work, a team effort, and I would recognize Giuseppe Dezzoli as my partner in crime, along with the Orlando team at ST Microelectronics. So we start with some motivation around the evolving landscape of neural processing architecture and hardware acceleration for NPU designs in general. And then we will dive deeper into the evolution of in-memory NPU architectures, specifically talk about the SRAM components that are driving some of these architectural innovation. I'll substantiate the claims on energy efficiency with sharing with you some of the silicon data that we've seen, and we'll follow up with mapping strategies, inference examples, before we conclude with some forward-looking statements. So basically, this community needs no introduction to this. Deep learning hardwares come in different forms and sizes, and they serve a wide range of workloads, from high-end cloud computing workloads all the way to tiny devices, which could be microcontroller, sensors with some amount of coupled neural processing capability. And they can handle a range of models all the way from pretty large models running both training and inference workloads to tiny workloads, predominantly inference workloads running at the edge. Now, when we look at this large space, we also see that this large architectural space has many different flavors and architectural templates, which are essentially plotted on this slide. The y-axis here represents the performance mentioned in gigaops per second, and the x-axis is the absolute power consumption mentioned in watts. And what you see is that across the range, moving from data center to extremely low power applications, the class of architectures you see in terms of neural processing architectures, most of them have a data flow dominant component. There are some architectures which have a mix of processor, DSP, and GPU. Some architectures have monolithic flavors of homogeneous in-memory computing only. And essentially, the mix of all of these architecture templates plays a huge role of how you're positioning your hardware in terms of its compute and power budget, right? Loosely represented by an energy efficiency metric measured in TOPS per watt. Now, when we look at edge and as a focus for ST Microelectronics, our focus is essentially to focus around this area where we are looking at having low power neural processing capabilities. At the same time, we are pushing for increasing performance without necessarily changing the power and the thermal budget of these devices. Now, when you're trying to do this, you're essentially trying to push the figure of merit I mentioned before, which is TOPS per watt. And to do this, you have to start to understand what are the different components that are contributing to energy consumption of these devices. And once we establish that, we look at what could be done to improve this, not by a small amount, but by what is needed to push this by an order of magnitude and beyond. So with that motivation, and this is just a refresher, if you look at deep learning hardware and compute density and energy efficiency being a key figure of merit that we measure, it's not an ideal merit. But this is still a way to compare two different architectural solutions. And when you start to map the different components that make up this choice of processing element is an important one. Most of these architectures exploit some form of parallelism. So the processing elements do present themselves in some kind of a spatial architecture. But what that processing element itself is could be significantly different. And so identifying what that is an important aspect. The precision range is an important one as well. When you're trying to look at edge inference or tinyML inference workloads, you probably are looking at quantized and reduced precision arithmetic. Does your architecture support it natively? Is it efficient as you scale arithmetic layer by layer? All of these things make a huge impact in terms of what you get as a figure of merit in compute density and energy efficiency. How these things are configured in terms of to deploy it over a large range of neural network architectures. You could create something which is fixed function, does very good for that specific workload, but with the kind of workloads we see even on edge hardware, changing and evolving rapidly, you need certain amount of reconfigurability to take care of a wide range of NN architectures. So that's another aspect, how reconfigurable you are. And then most importantly, how is the memory organized around the compute resources? Is this memory close enough? Is it on chip? Is it off chip? A lot of that access and efficiency of access determines how your system end-to-end performance behaves. And if you look at a range of embedded AI architectures, and the ones mentioned here are mostly digital neural processing unit architectures, work from NVIDIA, Google's focus around their HTPU, some amount of seminal academic work in the space of neural processing. And what's presented here is ST's neural processing architecture, referring to a paper which was the seminal work, which now has led to these solutions being in our products. And all of these different embedded AI architectures do have some form of a data flow component, but then use and extract parallelism quite differently. Irrespective of the difference, there is a fundamental limit to how much energy efficiency they can achieve. And when we try to look at what that performance is, you also have to see what is the evolution of the NPU. Starting from the left, being purely a software-driven workload. This is essentially a microcontroller which has no hardware acceleration capability. Most of the neural network execution is running in software. While this is good and can enable a lot of applications, a lot of tinyML applications, but not only. If you're pushing for extreme form of compute density or energy efficiency, you most likely will have moving to a neural processing architecture, which would have either memory outside the chip or would have a significant amount of resident memory on chip. Now, this is the class of solutions we saw in the previous slides. So this is now commodity. We see many providers having these class of solutions. They are enabling the edge performance significantly. But in terms of an architectural opportunity to achieve better energy efficiency, we are hitting a limit. And in the following slides, we quantify this a little more. And so if we have to move beyond this, and this cartoon is just implying what that next step is to eventually further merge the compute and the memory in an NPU, which is basically an architecture which is eliminating the so-called compute memory bottleneck and trying to have all the reconfigurability that we talked about. This was important. And by trying to do this by doing this computation in memory. Now that's in-memory computing, it is an overloaded word. And so I would like to just take a minute to define taxonomy on in-memory compute so that we can easily establish what we're talking about here. And you found in-memory computing solutions are typically seen in two flavors. There is analog in-memory computing and digital in-memory computing. Analog in-memory computing is where you're basically using the internals of a memory array and trying to do the multiplication and accumulation operations predominantly in analog domain. These things could be charge sharing or current summation operations happening on the bit line of the memory arrays itself. While some of these do present a good opportunity of reducing the energy cost of these operations, they also suffer from many analog circuit constraints related to variability, limited throughput wherever you do data conversion. And then there is also the associated complexity when it comes to defining built-in self-test or functional screening scenarios for these solutions. Digital in-memory computing, on the other hand, are still in-memory computing solutions, but implemented in a way that they are deterministic. They do not have any variability or approximate computing nature. They are compatible to data flow solutions. Because they're designed using pushed rule bit cells, they tend to be denser and present natively a duality that the same computing resource can be used as a traditional memory when it is not required to be configured as computational. But when it does need to be configured as computational resources, this can be done at runtime. Most of these solutions, given that they are digital in nature, do present also voltage and frequency scaling opportunities, much like digital hardware does. And in the end, some of this could be simpler to integrate to more traditional design, screening, and safety needs, which is important from product engineering perspective. Now, With that being an evolution, and we've seen this historical view, and what we're seeing now is this transition from pure digital NPU to a new class of NPU architectures exploiting in-memory computing. And why we're doing this is because we are probably hitting a limit of what we could do around energy efficiency. Now, this is a tinyML focused talk, and we are very particular in this community when it comes to low power. And what I'm presenting here is essentially, if you focus on energy efficiency, you do get that low power, but you also get scalability when you need to increase the performance of your system, and this could be quite dynamic based on the complexity of what you're handling. And so we stick to energy efficiency as a key metric to evaluate some of our solutions, even if low power is the focus. And what's seen here is essentially a breakup of what happens within an NPU and what are the different compute elements contributing to in terms of power. Shown on the top left is basically a subsystem view, which is where we break up on a workload how much is power spent in the NPU core itself, the NPU, the bus interconnect fabric around it, some of the system memory resources, and the host processor, which might be managing the runtime for the execution on this NPU. On its right is a lower level hierarchy, which is just the NPU, and now we're not talking about the AI subsystem. And within this, we see that a significant amount of this is spent on the core, which is the computational core, and the rest is spent on buffer accesses, which could be kernel buffers, DMA buffers, feature buffers that's required to orchestrate an end-to-end execution. And further within the computational core of the NPU, which is basically where most of all the math is happening, both vector operations, matrix multiplication operations, scalar operations. The bulk of it is used by matrix multiplication or convolutional operations. That's where most of the energy is spent. And if you're trying to deploy a device at the edge, you are basically not going to be going for very pushed silicon technology nodes. Digital scaling is a benefit you would attain, but because these are cost-conscious devices, process technology doesn't go to the leading edge of CMOS process. Now, when you consider that, most of these NPU architectural styles are already exploiting data flow, precision variability, sparsity supports, compression of weights, all the tricks in the book, including modes to exploit stationary properties of input, feature maps, weight, or output stationary executions. You see that given these technology nodes, you're starting to find that you fundamentally hit a bottleneck in terms of energy efficiency. Whatever you do, it's difficult generically. Now you can find an extreme example of exploiting sparsity and have someone talk about a better energy efficiency. But in general, across a range of workloads, 5 teraops per watt is where you start to see a bottleneck in these technology nodes. Now, what some of the needs, which are either coming from a perspective of operating within a certain power budget, or coming from a perspective of energy efficiency scalability in your solution, what we're seeing is the need to have something like an order of magnitude and more improvement in energy efficiency expected from AI at the edge over the next 5 years. Now, given that we are not changing technology nodes and we've kind of exploited many architectural tricks and innovations, we have to think differently. And that's basically the motivation to look at neural processing with in-memory computing, right? So looking at neural processors which are natively supporting IMs. So hopefully I've convinced you that we cannot be getting scalability out of our digital NPU architectures as easily as we might have when architectural solutions were still evolving, technology scaling was still allowing us, but both of these things are, at least for these class of edge devices, are not low-hanging fruits anymore. So what does an in-memory NPU look like? And kind of shown here is All of this in context of a prototype system on chip. It's a pretty canonical architecture if you look at edge devices. Has some class of a Cortex-M host processor, traditional components for the system, clocking factory, reset factory, system components like system DMAs, a range of high and low speed peripherals, external memory controllers, and a hierarchy of shared on-chip memory. Now, all of these are connected to some form of a system interconnect, which hosts, in this case, and we'll talk about silicon data to kind of create some reference of what these numbers and figure of merits are today with these class of architectures. This has about 8 different in-memory NPU subsystems, and we can kind of understand deeper on what they are. And put together, they kind of present a system which has scalability to look at small, tiny workloads. And on need, they could actually provide significant compute capability to run fairly complicated multimodal workloads as well, as we will see in the coming slides. So what's inside one of these IMNPU, which is short for in-memory neural processing unit, accelerator subsystem. And what you see is traditional components, and we will define them better, what these basic in-memory computing tiles look like. They're essentially doing most of the heavy lifting in terms of the math. But to execute genuine workloads, you don't need just matrix multiplication. You need a sophisticated set of data orchestration, mixing matrix multiplication and scalar operations. And to do that, you need, in this case, a low-cost, highly efficient interconnect. This is in this scenario because of the data flow nature is a streaming switch. Specialized DMAs that allow you to do tensor processing. Control units to manage each of these IMNPU subsystems, and then some form of autonomy to be able to manage its own runtime and execution. All of this is wrapped up in standard bus, high-performance bus interfaces, so they can go and sit on a more traditional system interconnect. Now, within these cluster subsystems, these computational tiles, which is the in-memory computing tiles, are associated with the tile itself, which I said is doing the matrix multiplication, but is also accompanying buffers, essentially feature buffer, partial sum buffers. And most of these solutions have multiple of these tiles. So the example here shown is with 8 tiles in one of these cluster subsystems. And these things can be connected to process data by picking up independent partial sums, combining them together, and then reusing a single DMA to push this data out to many different scenarios where we could look at parallel executions of chains of 2 to increase the execution parallelism and further chaining, to an extreme where you might have 2 parallel chains of 4 tiles, which are all cascaded together. And then the output is combined and then shared out through one single streaming DMA. Now, what it's important to notice that what we're trying to do here is not only look at maximizing data reuse, we're also trying to minimize the need for internal scratchpad memory. Chaining operations essentially are trying to send the output where it's actually required, making sure that the energy you consume in trying to move data from one computational element to the other is minimized. And more importantly, you're not unnecessarily accessing a system memory, which is being used just as a scratchpad buffer. So that's a waste of system resources and very expensive in terms of energy consumption. And what it does is wherever you're successful in doing this, not only your energy consumption is down, but you can also size your system very differently in terms of the need for scratchpad memory. Now, we talked about the general orchestration around this, but what is internally inside the IMC components? It's shown as an example here. And it's okay, if this community is not a circuits community. What you're looking at is a memory array a memory more traditionally is a sequential write and a sequential read device. And what we're trying to do when we are basically optimizing and factoring in this memory as an IMC resource, we are still leveraging the same basic building blocks in terms of the foundry bit cell. This is using, for those who are interested, this is using an 8T, one read, one write SRAM bit cell. But it is configured in a way where it is exploiting a lot of parallelism when it comes to computational mode, so that you can still have this device sequentially written to, in terms of weights are written sequentially. But once you have the weights written and you're doing some form of a weight stationary paradigm, I'm not saying this is a truly weight stationary architectures. Research has shown that true weight stationary architectures have very low execution efficiency. So here we are assuming that you could write and refresh these weights, but given the time that they will be stationary for, you would be extracting a huge amount of parallelism in terms of the computational operations that are happening on these resident weights, while the feature is flowing through this computational element. So that's the difference of a traditional memory from an in-memory computing orchestration. The writes are always sequential, but the reads and the computations are substantially parallelized when it comes to IMC mode. And what it does, it provides you not only access in terms of the parallelism I mentioned, you could also control this in terms of how the memory architectures are banked. All these MAC operations or convolution operations are happening internally. They're recombined within the memory resource itself. And what you get is a final partial sum. In the case where your tensors are not exactly fitting, you could be doing many different slicing techniques to create full or subtensor mode support. And whatever is the unutilized space in the computational element can be actually gated, so you're not basically burning power for no good reason. Essentially, and this is, remember, this is digital in-memory computing. So one of the things is that the computational operations and the final accumulation is all happening in full precision. So from an execution resolution, from a determinism point of view, this could be as much as running on digital hardware or running in software. Yeah? You're not compromising on the resolution of any of this execution. Now, what does this get, right? So we kind of reestablished that we are building upon a data flow paradigm. We're pushing most of the computational, we're the expensive ones in the memory. We are leveraging the memory through an extensive form of parallelism, which is exploitable in terms of neural network architectures. And for all of this, we are basically trying to do this for improving the so-called bottleneck we were seeing in terms of energy efficiency. So shown here are some of the measured silicon results of these class of architectures. And this is in a technology internal to ST Microelectronics. It's an 18 nanometer node, which has the capability to have an individual body bias control. So it's one of our FDSOI technologies. And what's shown here is measurement of energy efficiency on this architecture running end-to-end workloads. And you see two things. One, across a range of sparsity and transition, and we all know that these are knobs to be exploited. For a resolution of 4-bit symmetric weights and feature, which is basically when you're pushing for energy efficiency, we see there's a lot of 8-bit is the default. There's a lot of direction to move to 4 bits, and it might not be solving for all the layers, but majority of them can be served well at 4-bit resolution. So this is just a data point taken for defining energy efficiency. And what you see is, if you look at a single tile, and as you exploit sparsity, you see that the energy efficiency numbers of single atomic tiles are reaching some pretty impressive numbers of 500 tops per watt for 1 bit, and about 100 to 180 tops per watt for 4-bit resolution. What's important to note is, and from a research community, this was so-called confusion for the last couple of years, where atomic performances were quite interesting, but what we really want is an end-to-end system performance. So what's shown here is the full cluster performance, which is not just the tiles, it is all the other scalar logics, the data movers, the interconnects, and everything that you need to actually run an end-to-end NN. And what you see is, while these numbers, thanks to the in-memory computing flavors, can reach a peak performance close to 300 tops per watt for binary resolution, to about approximating 80 tops per watt for 4-bit. You see another trend, which is the trend of diminishing returns. That after a certain point, it doesn't matter how good the basic atomic tile is in terms of energy efficiency. You see other system of components, weighing over, and they basically become the bottleneck to what you can push for energy efficiency. Now, and what I'm trying to highlight here is, yes, you should focus on the in-memory computing components. They are important. They do a lot of the heavy lifting, but the orchestration of the rest of the system is equally important. And then after a certain point, that is what determines what you would get at the end level. Right? So this is an important trend to see when we look at systems using in-memory computing. This slide is just further elaborating that if you have a silicon technology which is focused on low power, in this case, the FDSOI 18 nanometer technology, which is internal to ST, and if you can control, in this case, you're controlling the forward body bias, which is essentially a way to modulate the VT of your device and get improved performance. And this is shown by this graph in the red, that when you don't need too much, you have no body bias, no forward body bias. And when you're trying to push for performance, going up to a body bias of 1.5 volts, you can get almost a 2x gain in terms of compute capability, with almost just a 14-15% degradation in terms of energy efficiency. Now, what this means is that dynamically, based on your application needs, you can get almost 2x performance on tap with only a marginal impact in terms of dynamic power. And this allows you to choose different operating points for your design based on the complexity of the workload, the mode you need to operate in. And now you have a general purpose hardware which can kind of function like a tinyML execution profile. But for needs where your scenes are dynamic and the requirements can change even momentarily, you could actually have significant amount of performance boosts available. This is just showing another knob of how compute density behaves, but let's focus on energy efficiency. And using the technology of this nature, you can bring a significant improvement and flexibility in these class of solutions. I promise this is real silicon data. So this is the chip micrograph. And to summarize this chip, which is multiple, and in particular 8 multi-tile IMNPU clusters. This operates at a wide operating range, has precision modes which support 1 to 4 bits. And in cases that we need 8 bits, it's possible to scale these solutions to 8 bits. There's nothing fundamentally limiting it. And what you see is you can get peak performances of about up to 57 teraops. When you're pushing for performance, you're obviously running it at higher voltage, your body bias values are higher. So this is the peak performance numbers that this computational hardware can get. And in 1 bit, this is obviously much larger. In this class of architecture, it's almost scaling linearly. But while you're achieving this, the same solutions are capable of energy efficiency numbers of about 77 tops per watt for 4-bit and crossing 300 tops per watt for 1 bit. Now, what it does is essentially 3 things. It gives you that flexibility of peak performance, peak compute capability, thanks to the high compute density these solutions have, and allows you to also have a very high energy efficiency and modulate where you operate based on the need of your application. And we'll see this in some of the coming slides, where we kind of orchestrate some system scenarios on seeing how we exploit something of this nature. Right? So you don't have to trade off one for the other. It's basically what I'm trying to say. So with that, as a background on the APU architectures, some details on the IMC components, and looking at how this all orchestrated and measured on silicon looks like, some of the mapping strategies that are required to optimize a solution for an IMC capable hardware has multiple dimensions. You obviously are looking at quantization support and aggressively leveraging this without necessarily saying everything needs to be homogeneous. So there's a range of precision in which you want to operate. You're exploiting weight compression, on the fly decompression to maximize both the storage efficiency on chip and off chip. Similarly, on similar techniques on the feature data, exploiting sparsity, mostly in a structured format. We've seen that structured sparsity is far more efficient to exploit as opposed to unstructured sparsity. And then looking at several solutions related to layer fusion, slicing approaches, whether it's kernel-wise, depth-wise, support for striping and striding, is all required to make sure that this kind of a spatial architecture can be used efficiently. Many solutions around kernel feature broadcasting, layout optimizations, relayouting engines, which kind of do geometry transformations from one layer to other, are all very important aspects to make sure that the IMC solutions maximize true ops per cycle. And then data movement, for instance, is not a limitation for the low efficiency of these class of architectures. So what message is, IMC is important, and it's a necessary component. It's not sufficient. You have to look at the full end-to-end solution in terms of making sure that that efficiency is actually deliverable on real workloads. An example here is of a reduced version of VGG16. We call it tiny VGG16. And what's shown is a scenario where you would be running all of these in a symmetric 8-bit resolution, as opposed to looking at a mixed precision mapping, where based on the need, you would have a variable set of resolution. And you see typically the input layers are running at higher resolutions, and the layers further down more amenable to precision reduction without too much of an accuracy impact. And if you look at all of these techniques and hardware capable of running mixed precision, supporting compression both for feature and weights, you can see that with the marginal accuracy loss of 1 to 3%, as opposed to a native 8-bit as a baseline, you could, depending on the actual data, could have anywhere up to 7x improvement in performance with just a marginal 1 to 3% impact in accuracy. So if you have in hardware and this kind of an accuracy loss is quite nominal mostly, you could be exploiting this and getting a significant performance computational boost. Now, I did mention in the previous section that many of these solutions, while they depend on the capability and efficiency of these individual IMC tiles, they need careful orchestration. And some of the examples here are just showing a case where you have a case where the same kernel is being used across multiple tiles. Weights are essentially broadcasted using rate broadcasting DMAs. And you have different streams processing your input feature volume. And essentially within one of these groups, you have these components chained. So you can see striping and chaining happening together in this cartoon on the same kernel data, which at the end is then written out as separate output volumes using separate DMA streams. This is also an orchestration, which is in this case using different kernels across these tile groups. You would still see the weight sharing DMAs. You will have separate input broadcasting DMAs, but these two different tile groups are then handling different parts of the output feature volume using separate DMAs, or in cases this could also be combined and muxed together to be written out using a single DMA, essentially sharing and merging this output stream. So the point to show these examples is to say that these kind of orchestration flexibility is what you need. And you should not be conceiving an in-memory NPU architecture as a monolithic component with very limited capabilities of interaction between one tile and how these tile groups can be combined, both in terms of input as well as output aggregation. Now with some more intuition around this, we look at inference examples on this computational hardware. Remember, we have 8 IMNPU clusters. Each cluster has multiple tiles. And shown is, in this case, a VGG16 style network mapping on one cluster and then using all 8 clusters. This is running at a really low voltage, still reasonable performance thanks to the forward body bias boost. And what you see is, for this class of a workload, even with one cluster, you could be running in excess of 600 inference per second, and this is substantially higher with all 8 clusters deployed. Now, the point here is not to say that this level of inference per second is what you need, but it's just a way to benchmark that on a single use case with reasonable complexity. If you have this level of performance at tap, still at a very energy efficient operating point, you could be easily deploying this hardware over multimodal use cases. And those multimodal use cases will basically share the computational capability of this hardware and allow you to run reasonable frame rates, but with multimodality complexities. This is the same thing running on, for those of you who are familiar with YOLO and these class of vision networks. This is essentially running a tiny YOLO 2 variant. Similar numbers in terms of inference per second, both on single and all the clusters put together. And what's important, and I forgot to mention, is while we're doing all of this, the actual energy efficiency of this map workload is still sustained to be a very high number. 50 TOPS per watt for 4-bit resolution. On this, it was about 46 on the previous example. So not only are you getting this kind of performance availability, but thanks to the way this is orchestrated for energy efficiency, these numbers are still an order of magnitude higher than what you were doing in digital NPUs. And this is just an example for an application using staged inference. So imagine you have a smart camera application with an appropriately configured sensor, which is low power. What this is showing is, if you are looking at running a always-on workload, which is basically observing the scene and mostly defining if there is any kind of an activation event which requires a more higher fidelity network to be run, you could be running this VGG-like always-on system only on one of the clusters. The rest are all shut down, power gated at a fairly low frequency. There's no need for boosting it, so this body bias values are 0. And you could be running about workload of about 1.25 GOPS is what you get. And this could give you about 10 inference per second on this class of network, and with a total power consumption, which is in hundreds of microwatts. And if you need that there is an interesting wake up and the rest of the system needs to be woken up, you can bring all the 8 clusters up. They could still be running at a fairly nominal frequency, minimum amount of body bias. This could handle something like 10x the complexity, much higher frame rates. This will consume something in terms of milliwatts, but given that this wake up is not so frequent and the system is duty cycle, assuming a 1 to 100 duty cycling between the two, something like this could be managing, and this is factoring in memory resources, IO, clocking, an appropriate external sensor interface, weight storage and access from an on-chip NVM. This could be running on 2 AA batteries for almost a year in this kind of a staged inference workload. And this is an example of a case where you have a lot of performance available on tap, but you're still focused, given that you're focused on energy efficiency, you can be actually be looking at extremely low power execution of the whole end-to-end application. So to summarize, if you look at the trends and the need for neural compute, energy efficiency being a key figure of merit for edge tinyML devices, we have progressed from the software-only paradigm to digital hardware NPUs with memory, tightly coupled memory on chip, to in-memory computing NPUs. And what we showed today was with digital in-memory computing in SRAM, and this is a chip which has internal NVM. And you could achieve, in extreme cases, up to a 50x improvement compared to where the pure digital logic would lie. Obviously, this is highly dependent on the application, but an order of magnitude improvement is what you could definitely see as you scale from the traditional digital NPU architecture paradigm to moving to IM NPU. Now, given that these were digital and we didn't talk about analog in memory computing, which is another subject altogether, a very interesting one. But given that we talked about digital in memory computing in this talk, this NPU is purely deterministic, which means that this could be deployed for general purpose. You have an end customer has full determinism given the precision regime you're operating in, as if it was running in software. What it does mean, and we did not touch upon in this talk, was a significant focus, dedicated focus on compilation and optimization tools to make sure that neural network efficiency is exploited over such a complex spatial architecture. But if you look at all of these, and the trends are very promising to push energy efficiency beyond the fundamental limit which we were seeing on more traditional digital NPUs in more edge and tinyML deployable technology nodes. That said, that's the last of my slides. Thank you for your attention, and I'm happy to have any questions now or later through the different forums and modalities that Hitesh was saying. Again, thank you for your attention.
Yeah, that was really insightful, Nitin. So yeah, in-memory compute, I think that looks like the future. So I have a couple of questions, and there are some questions from the audience as well. So I will start off with a few of them. So Hitul Sangvi, he's asking if about 2/3 of energy is on convolution operations, how would embedding AI computes within memory chip help?
So let's understand this. So if 2/3 of the power consumption is in the convolution operation, Gitesh, come back on the last part of the question.
So I think the question is coming from the motivation part of your slide, in which I think you showed that 2/3 of energy, I mean, a big chunk of energy was coming from convolution. So how would, because then you should be focusing more on that part of computation rather than on memory.
Yeah.
So
no. As a matter of fact, and the first observation is the correct observation, and that is exactly the motivation for the in-memory computing, because what's happening in this is the convolution operations are expensive because you are moving a lot of data to and fro from the memory, right? It is not just the computational hardware per se, but it's also the data movement cost associated to that. And what in-memory computing is doing is it is trying to do the computation where the data resides. So fundamentally, it is providing you a significant boost in terms of the cost of this convolution operation has become much less in terms of its energy cost. And any associated data movement which was required for this computation to be done, right? This is not sitting in isolation. That cost is also reduced. So the motivation of showing the digital NPU breakup was essentially to see we are focusing on where the power is spent, which is in this convolutional accelerators. And to minimize this, we are basically making these operations far more efficient in the way they are embedded. And given they're so close to where data resides, the data movement cost to feed these computational resources, which is a significant cost, right? The amount of on-chip bandwidth you need just to feed these parallel computational architecture is significant. And that movement cost is also being minimized. And the two lead to this combination and improvement in energy efficiency. Very good question.
yeah, good one. So Yeah, moving on to another question. So, CTX who is asking, does CNN and LSTM RNN require different NPU architecture to support? So, different kinds of neural networks, would they require different NPU architectures? Would be a general question I would ask.
Yeah. So the answer is that, as I was mentioning, if you're looking at you know having a general purpose hardware deployed, you cannot be factoring that a certain kind of neural network would be running on it. And so what I was showing, these class of architecture templates can deploy CNNs, can deploy LSTMs, GRUs, transformers, and all the data orchestration and flexibility. If you remember the data movers and the complexity to associate computational tiles to data movers, geometrical transformations at the input and output of those is essentially to make sure that you do not have to cater to one class of algorithms or neural network topologies, and you are flexible to do both. So in this case, CNNs, RNNs in their flavors of LSTM GRUs, and the more recent transformers, these are all flexible if you have consider all of this upfront in these IMNPU architectures. And the one that I was talking about does that.
Okay, thank you. So one more question is, it's a question by Vincent. The two algorithms you have shown results are not representative of SOTA model. For example, you are not including depth-wise, point-wise structure or multi-attention head, which both require a lot of data manipulation in main local memory. So under this configuration, which is more realistic to real usage, I would suspect a decreasing of performance. So can you comment on that? And
Yeah. So
one more. Yeah, go ahead. Yeah.
is there an associated question to that?
Yeah, so there is one more on maybe this is associated one. So can you also comment on how silicon results compared to ML Commerce Inference Tiny recent results version 2? So I think he's talking about the benchmark, right?
Yeah. Yes. Right. So I think yeah. So these are good questions. So some of the state of the art mentions here, for example, we do have results also on the mobile net architectures, which are essentially more depth separable approaches, which was mentioned here. And we see a similar gain in many of those architectures as well. There's nothing fundamentally that these step separable solutions would not exploit. There is, and the same argument also is for transformers. Sometimes the pre-processing workloads can take a part of your energy budget. And so these figure of merits in terms of peak energy efficiency numbers will vary based on the workload you're using and the efficiency. In this specific architecture that that I was elaborating here, these numbers of achieving 50 tops per watt for these class of networks will change. But what stays quite representative is actually the order of magnitude improvement that we have compared to more traditional digital NPU architectures. As opposed to the second part of the question, we do not have on this specific hardware a very explicit mapping on the ML commons or the tinyML references, but there is an ongoing effort for many of our hardware solutions which are there in production to be presenting these benchmarks, and we regularly follow them. What's important to note here is if you look at this class of an NPU architecture, which has multiple in-memory computing units, these units are essentially SRAM based, so they are writable. It's not that this is following a strict weight stationary paradigm. And the fact that you could combine and chain them, they do actually scale very well to some of the state-of-the-art models as well. Some of the challenges that might have motivated this question is if you look at these architectures very monolithically, and this is seen sometimes in-memory computing solutions, which are using much larger arrays, many of them being analog in-memory computing. and the cost to write to these memories can be expensive. In this cases, some of these efficiency numbers fall more drastically. But if you can size your IMC components appropriately and have multiple of them with the approaches that I was mentioning in terms of data flow chaining, striping, you do extend a lot of efficiency through the other examples that were mentioned, depth separable class of architectures, transformers, multi-head attention models, and so forth. The numbers would be different. I'm not claiming that this is 50 tops per watt in all real world use cases. These numbers scale, but what we're also looking at the energy efficiency benefits also sustain.
Okay, all right. Yeah. So one more question is, how do you estimate size of feature buffer at design time?
Well, in this case, there is a certain amount of feature buffer allocation of the memory, which is done. The size of these buffers are essentially done in a way that you could feed the amount of computational hardware that you've deployed in that specific silicon. And wherever, and this is not a large buffer space, so to speak, right? Because we are assuming that feature is essentially streaming. So there is some amount of buffering, but for most of these cases, you would assume that this feature is coming from data. Feature data is coming from a sensor or some kind of a sensor post-processing is leading to this. So given that these are data flow architectures, there is no strict memory allocation which would be resident for the feature, right? So if it's coming from an image sensor, you are assuming that you have some kind of a raster scan way, which is kind of streaming this sensor output, and that eventually is being sent as your feature input for your NPU. You're obviously not doing any kind of batching like in traditional cloud class hardware. So this is mostly all batch one and further striped streaming input data. So the feature buffer sizing per se is not so particular. What you need to make sure is that you have the computational capability to manage the frame rate of a sensor or the multitude of sensors in case of multimodal execution.
Right. So basically the data is used as it comes. So we don't really need to buffer it and think about it. Yeah. Okay. All right. Thank you. There are a couple of more questions actually. Maybe we can take that. Maybe 4 or 5 more. Yeah.
Well,
so yeah. So there is, besides matrix multiplication and convolution, does this accelerator, what you are showing, does it support their atomic operations as well? Are they operations atomic, and which operations are available as atomic operations? So that is one more question.
All right. So I think what you mean by the accelerator might not be very obvious, because what I presented here was a full end-to-end in-memory neural processing solution. So if the focus was on the IMC tiles itself, so the in-memory computing tiles are essentially focused on matrix multiplication. That is essentially the bulk of the math operation that they do. This is also the solution which kind of brings extracts the maximum parallelism that an IMC like hardware will present. And that's where it is focused at. It obviously presents this with a range of precision support and has support for data flow striding at the input and output, and does support some form of activation functions also embedded. Beyond that, the IMNPU cluster that I was orchestrating has a lot of other components which do scalar operations. So there is obviously support for arithmetic operations, wide support for activation units, pooling operators, data movers, which would basically provide you to do many form of geometric operations. So everything that you would need to run today a modern workload is, most of them is supported. Now, there might be a case where you find an odd operation which is not accelerated in hardware. And in this case, this is tightly coupled to the host processor, which has some amount of vector and scalar capabilities to run those rather exotic operations in software. When that were to happen, performance were to drop. But for most of these common operations, like the ones I mentioned, that you need in an execution, these are all accelerated. The IMC part is mostly meant for the matrix multiplication and convolution operations.
So you're kind of trying to accelerate the frequent case and then, let it run faster. That's what I think it'll go.
Yeah, so the most of this is hardware accelerated. All of it is not in IMC. There's also a lot of digital scalar hardware, which is a tightly coupled resource to the IMNPU. And it's an important comment to make, which is what I was trying to also say, that you do not want a monolithic architecture, which is just IMC arrays. We've seen that these solutions can perform very well, but they need a very specifically tailored NN topology. What you see in the real world requires you to have a mix of IMC and other traditional digital components near the memory to make sure that you have a very wide range of coverage on real world workloads. All of them are still accelerated. And for the odd case where you don't have this in any form of acceleration, IMC or otherwise, you obviously have a fallback to go back to the software solution.
One more question is, does hardware accelerator NPU have dedicated buffer memory? I think they do have, right?
Yeah, that's right. They do have dedicated buffer memories, and if you remember the example slide I was showing, there was this notion of dedicated memories as kernel buffers, feature buffer. As a matter of fact, IMC memories are basically act as kernel buffers. You write into them, that's where your weights are resident. When you're computing it, the real chip based on which could be resources outside the NPU, and in this case, the shared memory can also act as kernel buffer.
Yeah. So there is a lot of interest in transformer algorithms, right? So
Sure.
do you have data on transformer algorithm implementation? So is that something that you tried?
Yes, we do. It was not presented here. Some of that data might not be public yet, but we do, and we do see that transformers present both for vision and NLP workloads present a significant form of modern day workloads. And as I said, IMC architectures of the nature that was explained, they do not have anything fundamentally limiting them in terms of their applications on transformers. It was not what I was presenting in this slide, but it's not an exclusion or a boundary or an extreme case from an efficiency point of view.
Right. So, one more question is there. Typical inference pipeline often has pre-processing operations like spectrogram. So can NPU also accelerate this pre-processing, or should it map to the microcontroller? So what is this NPU for? Will it be only for acceleration, or can it be done for the pre-processing the data as well?
Yeah. So most of these neural processing hardware is to accelerate neural networks. Now, what's been talked about is, for example, if it's an audio case, you need the MFCC implementation to be done as an input process before you run some kind of an RNN or some other form of a network on it. So the answer is it depends on your system on chip architecture, and NPU per se is not supporting accelerating these pre-processing steps because they're not standard. If you do believe that audio would be one of the use cases, a SOC would have some kind of an accelerator sitting before the NPU, kind of in the same data streaming fashion, which could accelerate this. If the need for frame rate is not so high and your host has enough capability, you might as well be running this in the microcontroller and the host processor. So the answer depends a lot on your application. NPUs typically would not have these pre-processing capabilities. And you would need either dedicated hardware or a substantial amount of allocation to some computing resource to do that.
Right. So that is one performance hit that would come in, right? During the pre-processing, probably.
That's right. So you have to be careful about what that pre-processing cost is. and it should not be exorbitant enough. It's almost like saying you have to be careful about how expensive your sensor is in terms of its energy consumption, right? And if you have a sensor which is not low power, or a pre-processing pipeline which is not optimized, absolutely your end-to-end system performance will be impacted.
Right. So system level view is very important here. Yeah.
Right.
One more question. How does digital compute in SRAM compare with those in NVM like Flash?
Okay, that's a good question. And some of these questions, Gitesh, require their due share of time to be answered properly.
Right.
But
Right.
it's a good question. And the short answer is most of the Flash and NVM based solution, right? Flash is a kind of an NVM. There are other forms of non-volatile memory storage. They are essentially analog in memory computing in most nature. SRAMs also have these two flavors. Once we talked about was digital. And at an atomic level, it all depends on what are you comparing. The figure of merit is compute density or energy efficiency. Some of these NVM solutions can present a significant improvement in terms of energy budgets if everything fits and can maintain a weight stationary paradigm. If it doesn't, then you have to somehow factor in the very expensive write to these NVM solutions, which is mostly a high voltage write operation. So it's very slow, it's quite expensive, and you obviously are hitting the endurance or limit of this media, which only has endurance to be written to as much number of times. And so it becomes a very complex scenario and you cannot do an apple-to-apple comparison between an SRAM, IMC, and a Flash. Most Flash solutions you will see are analog. They rely significantly on weight stationary. They are larger monolithic arrays to maximize some of these scenarios that I mentioned. And they also require specialized technology solutions to where they can be produced.
Yeah, thank you, Nitin. So one more question probably from my side I would like to ask is how critical is the focus on quantized neural networks and other techniques to exploit sparsity in the neural network execution, especially for the new in-memory NPU architectures, or in general for any NPU architecture? So what pairing they have?
Yeah, I think this is a very good question, Gitesh. Quantized neural networks, and this community knows this very well, are a strong driver when it is us trying to maintain a certain level of accuracy and reduce the operation count, both from a compute but also storage perspective, right? So in case of in-memory computing, this is even more applicable, because if you could run most of your execution within a limited regime, most of these solutions have a very good scalability in terms of operational scalability with precision. They can support, like in one of my examples, mixed precision execution. So different layers can have different precision. So you could have different level of operational throughput available based on the precision of choice. So support quantized neural networks would obviously run more efficiently. Variable quantization precision from layer to layer is often used to maximize this opportunity without sacrificing, the final resolution or accuracy of your NN workload. Essentially, sparsity kind of plays in this, because using sparsity, you could exploit a certain set of compression techniques. Using sparsity, you could look up what kind of a dynamic range or accumulation range you will be achieving, and you could be exploiting those things by structuring your data that only the non-sparse operations is what you cater to, and you're not spending a lot of assuming that you're doing some form of structured sparsity that is also quite easily exploitable in these spatial architectures.
So it would need some kind of manual intervention plus software intervention.
Not manual. I think all of these things are exploited, because we're talking about kernel sparsity here, right? So this is known upfront. So a lot of your compilation techniques leverage this. Your NN model pre-processing before it is actually sent to your backend compiler, those high-level optimizations are going to exploit this. And based on the sophistication of an end customer, the degree, how much you can push this varies, right? So in some cases, the teams which are highly specialized in quantizing neural networks without trading off too much on the accuracy of the task, and they can have much more to gain in this. All of this is supported eventually. The mixed precision part and everything is supported using compilation and optimization tools. Doing it by hand is a fairly complex process and not recommended.
Right. Okay, so I think we are at the end of our question answers. So thank you, Nitin. So that was very enlightening and insightful talk. We learned a lot. With this, now we come to end of this talk, and I would like to thank our strategic partners. And we have this strategic partners like Qualcomm, Sentient, making edge AI reality. We have Platinum strategic partners, Etros by Sony. We have Gold strategic partners, Analog Devices, ARM, Edge Impulse, Infineon, Inantera, Microsoft, Renesas, ST Microelectronics, Synaptics. We have other silver strategic partners as well. So with this, we come to end of this talk. And we would like to remind you of keeping track on all the websites on the tinyml.org and YouTube as well. And talk to you later.